Good morning, afternoon everyone. Today, we are diving into the critical initial phases of building effective supervised machine learning models, specifically focusing on regression tasks. Supervised learning, as you know, involves training a model on a dataset that contains both input features and corresponding output labels, allowing the model to learn the mapping from inputs to outputs. Regression, a subset of supervised learning, deals with predicting continuous numerical values, such as sales figures, prices, or temperatures, before we can even think about applying complex algorithms. A crucial step is data preprocessing. This involves cleaning and transforming our raw data into a format suitable for machine learning algorithms. Will cover several key areas. How to handle missing data. Effectively manage non-numeric or categorical features. Normalize and transform our data. Identify and treat outliers. Introduce the concept of feature engineering. And finally, prepare our data for model evaluation using a train-test split. To ground our discussion in a practical scenario, let's consider a common business problem. Predicting sales. Our goal is to predict the sales of various products across different big mart outlets. This isn't just an academic exercise. Accurate sales predictions enable businesses to optimize inventory, improve marketing strategies, and make better operational decisions. The dataset we'll be working with, Big Mart sales, contains several independent variables, or features, such as the maximum retail price of a product, its category, and characteristics of the outlet like its size and location type. The dependent variable, our target, is the actual sales figure for that product. Our ultimate objective is to construct a robust machine learning model that can effectively forecast these sales based on the given attributes, thereby empowering Big Mart to make smarter, data-driven choices. The very first step in any data science project is to load and get acquainted with our data. We'll be utilizing the Big Mart sales dataset for our demonstration. Once loaded, it's crucial to perform some initial data exploration. This involves examining the dataset structure, looking at the first few rows, and getting a summary of its columns. Commands like !info, !in pandas are invaluable here, as they tell us about the number of entries, the names of the columns, the count of non-null values in each column, and their respective data types. Furthermore, explicitly checking the data type of each column using a function like !dtypes is vital. This helps us distinguish between numerical features, which are ready for mathematical operations, and categorical features, which will require special handling before they can be used in most machine learning algorithms. This initial understanding forms the basis for all subsequent preprocessing steps. Now, let's address one of the most common challenges in real-world datasets. Missing values. What exactly are they? Simply put, a missing value is an instance where a particular piece of information is absent or unrecorded for a given observation. These gaps can arise for a multitude of reasons. Perhaps the data was corrupted during transfer. There were errors during data collection. Certain information was not available at the time of recording, or even due to privacy regulations. Regardless of the cause, the critical point is that most machine learning algorithms are not designed to handle missing values directly. Feeding raw data with nans or empty strings to a model will typically result in errors or, at best, produce unreliable predictions. Therefore, identifying and appropriately handling these missing values is not just a good practice. It's an absolutely mandatory step in the data preprocessing pipeline to ensure our models can learn effectively. When we talk about missing values, It's helpful to categorize them into two main types: standard and non-standard. Standard missing values are those that are universally recognized by data analysis libraries, such as pandas in Python. These typically include representations like none for not a number, none, or null. These are straightforward to detect using built-in functions, as the tools are designed to interpret them as missing. However, real-world data is rarely that clean. We often encounter non-standard missing values, which are represented by arbitrary characters or strings that are not inherently recognized as missing by our tools. Examples include question marks, double hyphens, NA, unknown, or even specific numerical placeholders like 999 or -1 that signify missingness. The challenge with non-standard values is that they won't show up in our initial missing value counts unless we explicitly tell our tools what to look for and convert them into a standard missing format like none. This step is crucial to ensure we don't overlook any missingness that could skew our analysis. Let's apply this to our big MART dataset. When we perform a basic check for missing values using a common function like "df is null .sum", we can quickly identify columns with standard missing values. In our big MART data, we observe that item_weight, outlet_size, and outlet_location_type are indeed reported as having missing entries. These are the values that pandas automatically recognizes as missing. However, we also need to be vigilant for non-standard missing values. This often involves looking at unique values within categorical columns or scanning numerical columns for unusual placeholders. If we find any, say, an na string in a column that should contain numbers, our next step is to convert these non-standard representations into standard NaN values. This conversion ensures that all missing data, regardless of its original representation, is uniformly treated, simplifying subsequent imputation or removal processes. It's a critical step to ensure our dataset truly reflects all instances of missing information. Beyond just counting missing values, visualizing them can provide deeper insights into their patterns and distribution. A powerful tool for this is a heat map. By plotting the nullity of our dataset, where one color represents a present value and another represents a missing value, we can quickly grasp which columns are most affected and if there are any relationships between missingness across different features. For instance, in our big MART dataset, a heat map would visually confirm the presence of missing data in item_weight, outlet_size, and outlet_location_type. The distinct lines or blocks on the map corresponding to these variables immediately highlight the extent of their missingness. This visual cue is often more impactful than just numbers, helping us prioritize which columns need attention and potentially revealing if data is missing, not at random, which could have implications for our imputation strategy. Once we've identified missing values, the next crucial step is deciding how to handle them. Broadly, our strategies fall into two categories: dropping the data or replacing it, also known as imputation. Dropping data means either removing entire rows that contain missing values, or removing entire columns if they have too many missing entries. While straightforward, this can lead to significant information loss. The alternative is imputation, where we estimate and fill in the missing values. This is often preferred as it retains more of our valuable data. For numerical variables, common imputation methods include replacing missing values with the mean or median of the column. For categorical variables, we often use the mode or most frequent category. The choice between these methods depends heavily on the nature of the data, the extent of missingness, and the potential impact on our model. Let's explore each of these in more detail. Let's delve into the dropping strategy. When should we consider dropping an entire column? This is typically reserved for variables that have an overwhelmingly high percentage of missing values. A common rule of thumb suggests if 60 to 70% or more of the data in a column is missing, it might be more detrimental to impute, and dropping the column could be a better option, especially if it's not a critical predictor. However, this also depends on domain knowledge. If a heavily missing column is known to be a strong predictor, we might explore advanced imputation techniques. Dropping rows with missing values, on the other hand, is generally approached with more caution. While it ensures a clean dataset, it can lead to a significant loss of valuable information, especially if missingness is widespread or not completely random. In our Big Mart dataset, after initial assessment, we found that none of the columns had such an extreme level of missingness that dropping them entirely was necessary. This gives us the flexibility to choose imputation methods, preserving as much data as possible for our model. Moving on to imputation. One effective strategy for categorical variables is to replace missing values with the most frequent class, also known as the mode. The rationale here is based on the assumption that if we don't know the specific category, the most probable category for a missing instance is the one that appears most often in the existing data. For example, if we have a categorical variable like outlet_size, and medium is the most common size among the non-missing entries, then we would fill all missing outlet_size values with medium. This method is simple to implement and can be quite effective when the missingness is random and the distribution of categories is skewed, meaning one category clearly dominates. It helps preserve the overall distribution of the categorical variable to some extent, preventing the loss of entire rows. For numerical variables, the most common imputation techniques involve using measures of central tendency, the mean or the median. Mean imputation involves replacing all missing values in a numerical column with the average value of that column. It's a straightforward method, but it can be sensitive to outliers. If your numerical feature has extreme values, the mean can be significantly pulled towards these outliers, leading to a biased imputation. In such cases, median imputation is often a more robust choice. The median represents the middle value in a sorted dataset, making it less affected by extreme values. Therefore, if your data exhibits skewness or contains outliers, replacing missing values with the median is generally recommended to provide a more representative estimate. For our item_weight variable, we would calculate either its mean or median and then use that value to fill in all the missing entries, ensuring the numerical integrity of the column. After applying our chosen imputation or dropping strategies, it's absolutely crucial to verify that our efforts have been successful. The best way to do this is to rerun our missing value detection checks. We would again use functions like _df is null.sum to confirm that the counts of missing values in the affected columns have now dropped to 0. For a visual confirmation, replotting the heat map of missing values should now show a completely uniform pattern, indicating no missing data points. This final check is vital because overlooking even a few remaining missing values can cause errors or unexpected behavior in subsequent steps or during model training. Once this verification is complete, we can be confident that our dataset is clean and robust. ready to move on to the next stages of preprocessing.